now, and we can do whatever you would like. I think checking whether we have some people online. Okay. Okay. So you do.
So I can share my screen. Okay.
Yeah.
So we can start now.
Yeah. Okay.
Okay. Yeah. Actually, Emil, thank you so much for this organization, and give us this great opportunity to give a brief presentation of our tutorial for our Pandat software. Actually, for this time, I think the brief tutorial will have two parts. For the first part, I briefly introduction the basic functions of our software, and for the second part, we will give you a few examples of how to use our software to solve the real industry problems. Okay. So at the beginning, first of all, I'd like to see just a few sentences about our company. As you know, I think the name of our company is Computherm. Actually, this is a spin-off company from UW Medicine, which is founded by Professor Chuang in 1996. Actually, in our company, we develop the Scaffold-based computational tools. We call it Pandat. For the applications in a broad field of material science and engineering. And we also work on the government projects, and sometimes we also collaborate with industry companies and institutions working on the challenge programs and with potential commercial payoffs. And our company located at Madison, Wisconsin. Probably, maybe some of you may not have been here. Actually, this is a little bit north part of the U.S. And during summer, it's very beautiful. This is a lakeside, but during winter time, most from the end of October to the April of next year, will be a lot of snow. It maybe look like this. If you plan to visit us, I think for the summer or the fall season, that will be much better. Okay. So this is our software. We call it the Pandat. This is an integrated computational platform we developed based on the Kafka approach. This is mainly for the multi-component phase diagram calculation and the materials property simulation. Some of you may also know some other similar software. Actually, the main advantages of our software over the others, there's three parts. For the first one, we have the robust thermodynamic calculation engine. This ensures us to obtain the accurate result. We also have our software also have a unified graphical user interface and a flexible post-calculation result editing function. Actually, all these functions enables our software is powerful and user-friendly. Also, you can see in our software, we call this an integrated platform. We use the modular design methodology. Right now, I think for our software, we have several modules. For the phase diagram module, this is for the phase diagram calculation and the thermodynamic property calculation. And we also have the precipitation module. For this one, it's for precipitation simulation. And for the diffusion module, it's for diffusion simulation. And this year, we also released a solidification module. This is for solidification simulation with considering the bank diffusion effect in the solid space. I will give you more detailed information later on. And this year, we are going to release a new module. This is for the phase field simulation. I will also give you some brief introduction of this module. And we also develop another function as a pan parser. You can use this function to call all the functions Pandas software, and also you can do the results visualization and analysis. I also will show you some results later on. Okay. Next, I will show you the basic functions of each module. Just give you a brief introduction. Actually, this is for the pan-phase diagram module. Here, just list some basic functions of the pan-phase diagram module. You can see we can do point calculation, line calculation, section calculation of all the others. I will briefly mention these functions in the next. So this is a typical composition and temperature boundary phase diagram for the aluminum magnesium system. This can be obtained from the section calculation. But we also can do line calculation when one variant is fixed. For example, we can fix the temperature. Then calculate the line calculation, we can calculate the property evolution with the change of the composition. When the composition is fixed, the property change of the alloy with the temperature can then be obtained as well. When we fix both alloy composition and temperature, I think we can then calculate the property at just one point. As we know, actually the ternary phase diagram is a triangular prism, which can be calculated as a 3D diagram. I will show you one example in next slide. But for each visualization, we usually use the isosome section, which is cut the triangular prism horizontally at a constant temperature, project into a 2D surface. Sometimes you just visual view like this. Also, we can also cut the triangular prism vertically at a certain direction. This is called isoplastic section. It will show like this. These two types of phase diagram are very important, especially in multi-component systems. And in this slide, for the right figure, this is a lattice projection of the aluminum magnesium zinc ternary system. I think for the calculated line in blue, this is divided this region in different regions. At each region, it shows the primary phase at this composition during solidification. And in contour, this is the isothermal lines. This is called lattice projection. This type of diagram is very important for the casting alloys. And as I mentioned previously, we can do the calculate the 3D diagram. This is a very unique feature of the software, and which if you have it's a long user to calculate 3D diagrams of any 3-component systems. This is just an example. Shows for the ABC hypothetical system. And in this slide, I just give you an example to calculate the solution path of the aluminum magnesium zinc alloy. Use 2 approximate models in a simple way without invoking complex kinetic calculations. One model is we call equilibrium or the level rule, as shown in the red line. The other model is non-equilibrium. We call it the shell model, as shown in the blue line. These two models are extremely simple. May not be able to accurately describe the real casting processing. So that's the reason we developed a more advanced the pan-solution module. I will give example later on. Actually, in the pan phase diagram model, the other unique feature is that we can plot contour lines of all kinds of available properties on the phase diagram. This diagram, I just use a titanium, aluminum, vanadium alloy as an example. This alloy, you can see of the minor addition of nitrogen and oxygen. This alloy, as we know, this is an alpha-beta alloy, and the fraction of the meaning the alloy composition mainly located in this region, and the fraction of the beta phase is very important for the alloy property. But from this diagram, we know the alloys what's the alloy composition and temperature the alloy can locate it in the two-phase region, but we cannot directly know the exact fraction of the beta phase. But with the calculated contour line, this is the contour line for the beta phase fraction, and you can superimpose in the same diagram as shown in the red lines. This is the number indicates the fraction of the beta phase. And from this type of calculations, we can then easily select the proper alloy composition and heat treat temperature to achieve the desired microstructure with a certain fraction of beta phase. For example, if we prefer for the beta phase to be fixed at 30%, which we align along this line, we can choose at what we can decide at which composition and which temperature we're able to obtain the 30% of a beta phase. So this information is very important for us to select the alloy composition and heat treatment temperature to achieve a certain fraction of alpha beta phase in the microstructure. This is very important for the alloy design. Of course, we can plot contour lines of all kinds of available properties on a phase diagram, such as surface tension, viscosity, electrical conductivity, etc. So this is very useful for alloy design to select an alloy composition with a design microstructure and other required physical properties. This is also very important for the alloy design. So that just give you the about slides just give you a brief introduction of the functions of the PAN phase diagram module. So the next part, few slides, I will show the functions of our PAN precipitation module. So this slide is just show you the basic function of the precipitation module. This module allows users to simulate the precipitate kinetics, such as the temporal evolution of the precipitate size, fraction, number density, and the particle size distribution. And we can also do co-precipitation to simulate the precipitation with more than one precipitate, and even those precipitates may be described by different types of kinetic models. Actually, our simulation can also consider different heterogeneous nucleation and as well as their morphology evolution. Actually, one of the most important parameters to do the precipitation simulation is the interfacial energy. Okay, actually, we also develop a function to help us to estimate the interfacial energy to do the precipitation simulation, which makes this module is much easier for the user to get started to use it. Actually, next I will just give you an example. Use this precipitation simulation of the 7-substance aluminum alloy as an example to demonstrate the valuable applications of the PAN precipitation module in the alloy design development. So this slide just shows the precipitation simulation for this aluminum alloy under this heat treatment condition. You can see this one described at the left-hand side just describe the microstructure. This is the particle size evolution. And for the line is our simulated result, and the symbols are the experimental result. So the right-hand diagram shows the property. This is for the yield strength. This is again, the line is our simulation. The symbols are the experimental result. You can see right now our simulation can well describe the experimental result. But here I would like to emphasize that's the most important advantage of this module. We can see we can use the same set of databases or the parameters we obtained for this alloy to perform virtual experiments for the same series of alloys in order to optimize alloy composition and the processing optimization. Okay, so use the same set of parameters obtained based on the previous experiment result. We can do virtual experiment. This virtual experiment, we try to change the heat treatment condition, such as aging temperature or the cooling rate. You can see the trend of the different heat treatment conditions. Using this kind of virtual experiment, you will help us to choose the proper aging temperature and cooling speed to obtain the optimized property of this alloy. We can also do virtual experiment to optimize the alloy composition. For example, we change the composition, either the magnesium or the zinc, to see the property change versus the composition. So based on these types of simulation, we can also optimize the alloy composition. So this is just one example, show you the valuable application of our this precipitation module. For the next module, we are going to introduce is the diffusion module. Actually, for the diffusion module, this is for diffusion simulation, and this slide just briefly lists the major functions of this module. We can do the different couple simulation, or some special processing, such as carbonizing, nitriding, dissolution, homogenization. We also can consider the various geometry features. So a few examples will be given in the next few slides to show the functions of this module. So this example is for the multi-component diffusion couple. This is for nickel-based alloy, the iron 100 and 718. For this alloy, you can see for the lines of simulation results, and the symbols are experimental measurements. So you can see this is the one application of this module for the diffusion couple. And the other example is for the homogenization of the one function. This is for the iron, chrome, nickel ternary alloys. So for the dotted profile, this is the original composition. We just use this one as the input. Then you can see after a certain of time what the composition change will be. Based on using this calculation, we know how long it will take for this alloy to be homogenized. This example is for carbonization. This figure shows the carbon concentration evolution versus this distance during carbonization. For this one, the simulation is for the tube with fixed environmental activity. So you can see that the carbon concentration change versus time. Of course, a user can assign different boundary conditions, such as you can fix the carbon composition or its flux as well. This is for the carbonization. Of course, on the other hand, user can also simulate decarbonizing processing by assign different boundary conditions to subtract carbon from substrate. So this figure just simulates the carbon depletion depth of the iron carbon binary alloys, which is heat treated at 17 degrees C. You can see the carbon depletion depth versus time of this alloy. This is for the decarbonization function. The other function we want to show is for the dissolution simulation using the pan diffusion module. This for the aluminum alloy. This for the Al2Cu the aluminum the theta phase. For the x-axis is time. The y-axis is particle size. You can see the dissolution processing of this phase during certain treatment at this temperature. So based on the above few slides, just give you a quick introduction of what kind of functions in the pan diffusion module. As I mentioned previously, for this year, we just released for the pan solidification module. For this module, we consider the back diffusion effect in a solid phase. Then we can make more reasonable and accurate prediction for the real casting processing. In this module, we can simulate the secondary dendron arm spacing evolution and the macro segregation evolution. And we, as I mentioned previously, in this module, we consider different effects such as back diffusion, auto cooling, and dendron arm space causing effects. So, with considering all these effects, the solution paths are more reasonable for the real casting processing. So, I just want to give you a quick background why we developed this module and what's the difference of this module to the solidification model already we mentioned previously in the phase diagram module. Okay, so usually, the solidification simulation in the Kappa approach, we just focus on the solid liquid phase region, as shown in this schematic diagram. In the pan phase diagram module, as we know, we already implemented the shell model, right? The shell model, the schematic is shown here. So this model has been well known how to deal with this one without considering the back diffusion in the solid phase, but the complex mixing in the liquid phase. This is schematic. In order to use this model, we just need the thermodynamic database. But in order to consider different back diffusion in the solid phase, we need to use a modified shell model. In order to, as the schematic diagram show here, the real kinetic processing is kind of complex. I won't go into too much detail, but in order to do this kind of simulation, we need not only the thermodynamic database, but also the mobility database and some solidification kinetic parameters in order to do this. Okay, this is just a brief background of numeric models using the pan solidification model. Next, I will just give you an example of the application of this model. So this is an example to show for the magnesium aluminum tin, the AT alloy. For example, the left-hand diagram shows the concentration evolution of this module. You see the line is our simulation result, and the symbols are the experiment. And on the right-hand diagram, it showed the comparison between the simulated and the experimentally measured secondary dendron arm spacing. You can see both the macro segregation concentration profile and the secondary dendron arm spacing can agree well with each other. This indicates the pan solidification simulation similar result is pretty good. I just want to later on I can show you more examples of this module, but here just give you a quick example of this module. Okay, as I mentioned previously, this year we are going to release a new module for the we call pan phase field. This for phase field simulation. If you want to know more detailed information, you can just pay attention to our website or newsletter. But here, I just want to quickly show you to apply to basic applications we have in this module. This is a precipitation simulation, phase field simulation for the gamma double prime precipitase growth. This is 2D simulation. This for just to give you show the evolution of the module. I think also both the for the visualization and the thing, I think all this module, all these functions have been integrated in our current software. You do not need to do anything else. Okay, this module has been built in our software. The other example, this is just to show you a 3D simulation for spinodal decomposition. This is for the 6 component alloy. You can see all the simulation conditions are listed here. This is the simulated result. In addition to here I would like to mention, in addition to the built-in models, user can also provide the tools and the platform for user to build to plug in their own models to do the phase field simulation. Okay, so the most important message I need to emphasize here is that using our current phase field model, we can directly couple the thermodynamic calculation with the phase field simulation with I think with a very good efficiency. Okay, just to give you 2 quick examples. I think at the end of introduction for the basic functions of Panda software, here I would like to use 1 slide to emphasize some advanced features of the Panda software. So the one of the advanced feature is in Panda software is we can run the Panda in the console mode without the graphical user interface, and this can allow user to facilitate the integration with the third-party software packages. The other advanced feature is we can perform high throughput calculation, which allow user to perform thousands of calculations altogether, and then do the data mining with defined criteria. And this can all be done in the using our high throughput calculation. At present, this function can be used in different modules, such as the phase diagram module, Precipitation module, and the pan solidification module. All these modules can use the high throughput calculation function. The other feature we would like to emphasize is we have a append database and user-defined property function. This function allows user to append a custom-made database to an original database. For example, you want to develop your own database, or you have some new data want to change the original database. This allows you to do it. Use this function. It's very also very powerful and useful. As I mentioned previously, we just developed the Python function, right? This function allows user to run all functions of Panda via the Python scripts. I think this Python is a very popular programming language. I think especially for the young people, they prefer to use it. I think you can use this one to run all functions of software. I think in our current developed Python function, this is open source. It's already allowing user to handle the concurrent or multi-thread high throughput calculations and perform data analysis, as well as visualization from all types of Panda calculation results. I think this also enables this open resource also can allow user to do further development to use this function or use this module. Okay, I think this is the first part of our presentation. I'm not sure how for the next part. I think we are going to just give you some brief introduction of real application by my colleague Songamo. Songamo, are you here?
Yeah.
Okay.
Yeah, I continue, or we discuss how we should discuss for the first part.
I think we can just go through everything.
Can I just make a remark in between you two? Yeah, just sorry for interrupting you. Just a second. So thank you for your presentation. It's very nice. Of course, I am since a little bit of time also a Pandat user, and I'm enjoying it, using it my students. and so on. The new thing for me is the Python module that I was not aware of. And so it's exciting that possibly, especially young people, not me, because I'm a little bit, I mean, unfortunately, I'm 57 and next to 58 years. So I believe, but it is very, very impressive. And the point is that. So these guys that are listening to you, they are basically in a way or the other related to the steel business. And the steel business, sometimes you need to do simulation for standard steels. Sometimes you need to design possibly new steels and blah, 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 blah. So the challenge is huge. The many phases that are present are huge. So my question is that apart from using possible Python applications, which would be fantastic, and maybe we should talk directly about this one. The point is that in the industry now, many guys are using so-called Industry 4.0 applications, and basically it's all some sort of, I would say, not multiple regressions, but neural networks applications, and there's something like. So I believe that there should be a strong basis for going on with Pandat as for steels. It's not an easy game. Professor Andre de Silva, then he will speak about something related to that. But I believe that for this big industry, because after all, for metals, steel, it is the #1 industry in the world, and it has something new to say as well. I think it would be nice to go on even in that direction, especially linking it to general purposes for the simulation, would say like metal forming applications, some special continuous casting applications, so on. So try to link. I know that you're already proposing to some software producers, some of basically API interfaces, but I would believe that the study of metallurgy would be complemented even to mechanical engineers, which usually they believe that when they are making their simulation, there is just the steel properties, they are just iron. And then the physical properties of iron, it's all that, so that they should learn when they are in university something that is something more complex, that's the phase analysis. So thank you for your interesting introduction. And let's go on, because we keep on the schedule that we have the last talk starting at in half an hour, roughly speaking, but I think we will have also Professor Andre somewhere. But so please somehow start if there is no other observation or question from other people here. Thank you for the moment.
Okay, yeah, thank you. And thank you for the introduction. Yeah, now I'll continue to present several examples on how to use Pandat in real alloy applications. The first example is about the hot cracking. Yeah, as we all know, the hot cracking are common defects generated in casting, welding, and additive manufacturing. The hot cracking is a complicated phenomenon occurred during the solidification of the alloys. And in order to understanding the mechanism of the hot cracking formation, many criteria have been developed to predict the hot cracking susceptibility of the alloys. But here now, I want to introduce a simple but effective criterion to evaluate the hot cracking susceptibility, what we call it as the crack susceptibility index. And this index is developed based on the feeding of the last stage of solidification. The CSI refers to the maximum value of dt dfs square root. And the T refers to the temperature, and the Fs is the solid fractions. And in more details, in the Professor Sindoko's 2015 paper, he provided a detailed scientific analysis and the derivations and the how and the why these parameters could present the cracking susceptibility. But here now I just want to mention is a brief mention about the DTDFS, why this could present the cracking susceptibility. From this diagram, we see is the DTDFS square root represent the feeding channel at the last stage of solidification. And this value is smaller, and then the feeding channel would be shorter, and it's easier to feeding and could feed and could not easy to present to generate the crack. But if the DTDFS square root is larger, and then it will have a longer channel, and the hot cracking will be easily to form. But at the same time, it's some alloys, and the DTDFS square root could continue until at the very end of solidification. But actually, in certain point, and the crack susceptibility could end, even though some liquid still exists. So Professor Ko proposed the square root of FAS should be less than 99%. So that is the basic idea of this criterion. And if we see how to generate these parameters, we're easily to get the T versus square root FAS from Panda calculation. And the CSI, this represent the slope of this curve. And when the slope has the largest value, which represent the CSI index of this alloy. So this criterion is very simple and it's very effective. So now I want to give you a result comparison with our Panda calculation and experimental work. This is aluminum alloy. It's aluminum copper magnesium alloy. From this result, we can see our calculated result in very good agreement with the experimental result, which is the right side. And we can also see from this result, we can also see the impact of copper and the impact of magnesium on the hot cracking susceptibility. And we see with increasing copper, the hot cracking it more tend to increase and then decrease. But with magnesium, it has much small impact on this hot cracking. This simulated result it also agree well with the experimental result. Here, I also need to mention is this the calculated map is a contour map, and which each point here in this map is represent each alloy composition. So if we need to do that calculations one by one, and to obtain the maximum slope of that tangent line of TFS square root manually one by one, then it's also time consuming. In our Panda software, as my colleague Dr. Chuang mentioned before, we have a high throughput calculations feature. We can do all these calculations with a simple composition setting, and then we calculated all these calculations, and through the high throughput calculation result analysis, we can generate the CSI of each alloy directly from the high throughput calculations and produce this contour map very easily. So this is an example on how to use Panda to do the simulation for the hot cracking. And if for more details, and you can refer to our example book 5.3. We have a example to demonstrate how to do this step by step. And this is, and also this calculation is performed in our Certification module. We considered the back diffusions. So for the shy and the equilibrium, we can also similar calculation can also do in phase field, phase diagram module. So that is the example of this. And the second example is about the green refinement. Yeah, we know green refinement has many benefits. And one of the most benefits is which can improve activity simultaneously. And to get the better green side or refined green side, normally we have two methods. One is through the nucleation. So we add effective nucleates to improve or to accelerate the nucleate of the alloy at the beginning of the solidification. Or we can add some alloy elements to improve the growth, to restrain the growth of the grains. For the growth part, have a very important factor, which we call it is growth restriction factor. Some people also call it a Q value. So if an alloy with a higher Q value, normally we expect this alloy would have a smaller grain size. So this is the background of the Q value or the growth restriction factor, GRF. And what is GRF? Traditionally, it is based on the phase diagram. And actually, the Q from all these parameters, M, C, K, is from the binary phase diagram. And the M is referred to the Richter slope, and the C is the composition or the solute content, and the K is the partition coefficient. So if we want to do multi-component alloys, traditionally we just to combine all these alloy elements with the main metric elements based on all these binary Q values and multiply them to obtain the multi-component alloys Q value. But that is not accurate, actually. So through the CAFAT method, we can do this calculation to obtain the Q value more accurate, which is based on the constitution undercooling. And use this, we can see no matter how many components you have, and use PANDAT or other CAFAT method, we can do this calculation for each alloy. And in PANDAT, we can directly calculate this dt dfs when the fs equals 0. So this value is referred to the real Q value of any multi-component alloys. So using the CAFAT method is not only easier, but also more importantly, it's more reliable. Now, I would like to give you a real example. In this paper, they investigated the elements alloy composition on the grain side of low density steels, which has aluminum, silicon, phosphorus, manganese, and copper, carbon. They published their result, calculated, measured grain size and calculated GRF value. We see this diagram. And the result is secondary. We cannot see too much strong tend to see the grain size, a relationship of grain size and the GRF value. But I use the same alloys and use our PANDAT calculations and use their grain size. I do it again, and we found if we use the CAFAT to calculate the real Q value or the GRF value, this trend is very clear. So this is the advantages of the CAFAT method for these Q value calculations. In our PANDAT, all these are one alloys, but if we want to analyze a lot of alloys, what the impact of the composition of in a larger composition range. So our Hasse-Put calculation is also helpful to obtain in a wider composition range to see the impact of the alloy on the GRF value. So this is an example of the Hasse-Put calculation of GRF value to show the steel, the impact of aluminum and silicon on the GRF value in steels. So we can see for the aluminum, the increase of aluminum has very little impact on the GRF value. It's even when you added about 10 weight percent, it's still less than 10. the GRF value is still less than 10. But on the other hand, the silicon has a much stronger impact here with increase in silicon, which the GRF value is increased up to here, it's almost 40. So this is an example to show how CAFAD method would be powerful to evaluate the GRF of different alloys. And also I need to mention here, and you see these calculations very fine. I do these calculations is with a step of 0.2. And in total of this diagram, I calculated more than 2,600 alloy compositions. And in our pandas, we do that calculation is about 40 minutes. It's also not very, very fast and very effective. So this is the second example on how to use Panda to do in the green refinement of alloys. And the third example is about the precipitation hardening. And we know is the 17 for precipitation hardening. Steels are commonly used in many application areas. And this alloy has 12 alloying elements. So it's a real multiple component alloy. And here we do, in Panda, we do the line calculations. We see different phases could be formed under equilibrium conditions. But for some kinetic reasons, we know it's during heat treatment, especially the aging heat treatment, the copper-rich precipitate is the main strengthening phase. But other phases, because of kinetic reasons, it's very difficult to form. For example, especially the sigma phase, even though the amount, the space equilibrium amount is a lot, but for kinetic reasons, it may be difficult to form. So in this example, I will show you our pan precipitation to simulate the precipitate of the copper, of the copper-rich hardening phase in this steel. And we know these alloys have two common aging temperature is 480 and 590. That is often used in applications. And in this paper, they also investigated the experimental work of this alloy had mass structure and property result. So we see using our pan precipitation, we can simulate the size of the precipitate evaluated with time, and we can also simulate the number of densities of the particles and the particle size distribution, which we see under two temperatures. And the 480 had a smaller size and the larger number of densities. And here is the particle size distribution is in a lower particle size area. If we compare with the experimental result, it's 480 has a larger density, number of densities, and also the smaller particle size. So, which is in a very reasonable agreement with their real experimental work. Besides the microstructure, we can also simulate the hardness. This is our simulated result at 480. The trend is very clear. It's 480 is much stronger than 590. So this is an example I want to show is the precipitation module. We can not only handle a simple case, we can also handle complicated multi-component alloys. And we can simulate both microstructure and mechanical properties, and which can produce reasonable result with experimental result. And here is we cannot only handle the precipitate with one phase. This example shows in iron, manganese, and carbon alloys had three precipitate different locations. One is in green boundary, and one is in through the dislocation. This is our simulated result. In this case, it just want to show you that we can also simulate the precipitate at different places and different nucleation mechanisms and multiple particle precipitations. So yeah, these three examples are essentially what I want to present today. Yeah, thank you for all your attention.
Thank you to you, Songamo. Very, very valuable presentation, as long as many of your scientific papers I have been reading over the years. So this is something very nice. And to be honest, with my students, we've been using your Pandat software for the crack susceptibility index and also for the growth restriction factor. And we are using it at lessons at, let's say, at the student level. But my ambition, you see there on the chat, is to exploit these tools and maybe in a more scientific way to propose with a special number of metals. Zhang, she knows because she's been invited. And we will have a special issue with my colleague and friend Maria Ballard. She's from Brunel University, BCAST group, and we have been investigating in copper alloys some of her practical results, and we've been using those concepts to go on. Now, my impression is that possibly using simple simulations about crack formation in continuous casting, I think it would be fantastic. And you've been also giving us very nice examples, for instance, for this 17.4 pH steel, which is very interesting and appealing, especially for people doing now with 3D printing so there is a lot of things to go on. And also this one about lightweight steels has been enlightening. So it has been a very nice couple of lectures of both of you. And I hope we will be going on for collaborations and so on. This is a very nice example of CALFA, the concepts and tools to be applied to different practical metallurgical examples. So I wish you a big success for the future, that we can produce, or you can produce, not only scientific results, but you can produce applications which are useful in the world of steel, which is a complex and world, but I believe it is totally worth. Okay, yeah. Thank you.
Okay. Thank you.
And,
thank you.
Thank you to all of you. If there is any sort of question, so I believe that if some of you, I mean, I'm using Pandat every year with my students. I'm using in the course of metallurgy, we are devoting at least I would say 20% of the time at least to learn how to use Pandat with 3 components, which we know which is free. Then to the students, I distribute some open databases for steel, for aluminum, for copper. One of copper I developed by myself. I think it is the most wide open, which is not so precise, open database in the world. And we've been using it for a project for semi-solid casting of metal alloys with my dear friend Fabio Giolo, who's not any longer with us, unfortunately. And so, thank you for all. We will keep in contact. Maybe we will try to link your knowledge and your ongoing knowledge, because I see from time to time, from month to month, that you are going on, and I think it's very interesting to have the possibility to cooperate with you, and because we have this direct link. So I'm inviting you, especially you, Chuang and Songamo, to consider this possible publication. I'm the guest editor of this metals number, and I hope also Andrea Costa Silva, which I hope he will be with us now. Andre, are you with us now?
Yes,
okay.
I'm here.
Okay. So we can switch now, and we can leave all your new experience about using this team software. So we know that you are a very good user of both Calfa tools. I think you are a thermocalc basically user, but you have also very good experience in the characterization of steels. Actually, it was very surprising. Revision of the book on metallography has so very good comments from Brazil. I think all the Brazilian metallographers, they are fond of your revision book. It's very, very something special. I can tell you that I will recommend my students to get the book they can afford to, but because it's something around 20 euros, so any of my students can afford to buy it. It's not very expensive. They can download it for real money from the internet without using some sort of tricks. And I think it's very useful to use it and recommend it to anyone. Luckily, we Italians, we can understand Portuguese. And so, so it's very useful for all of us. Of course, there is the AESM publication, which is a little bit more expensive. So I will get it for my library, but I cannot expect my students to get it for around 200 something dollars or euros, but they can afford for sure to buy your book in the Google Books application, and maybe in the future I would love to have it in Italian. Maybe I will try to evolve. I mean, get some would say postdoc or the like, and giving them some money, because it would be so nice to have the Italian translation of your in Italian, because I think Brazil is something special, something, and your knowledge about steels is really surprising. I mean, it's something that that they don't have any longer in many other places. So please have your communication with switch off the phone. If you make any communication mistake, no problems, because we are all here for you, and we are so pleased that you have you here. Okay.
Okay. Thank you so much, Fabio. Can you hear me? Yes.
Yes.
Yeah.
Okay.
Sure, we can hear.
Yeah. So I will try to present. Well, first about the book. I mean, the book was written initially in 1951, and it was the textbook we use here for ages. And then I was invited to revise it in 2008, and it was for me a great honor and pleasure to be able to revise such a classical book. So, of course, I included some new information, as you have seen, but it's real nice. I mean, I still believe that the best way to do steels involves being able to put together metallography, thermodynamics, and actual work, because there's a lot of just simulation going around, and it's really nice when you can do putting the two things together, like the colleague from Penn Data showed. I mean, there's a lot of interesting work that can be done putting together the real experience, experimental work, and the calculations. So I will try to stream the presentation I have recorded, and if it doesn't come out well, then I can try to present it myself, because I have, I mean, here is like 1:30 in the afternoon, so it's a pretty busy time. But let's see if I can get this shown, and if you have any trouble seeing the presentation, please just let me know, okay? Can you all see my screen now?
Yeah.
Can you see?
Sure.
Okay.
Yeah, yeah.
So here we go.
Excuse me, can you all hear? I have low voice. I cannot hear.
We have still the problem of not hearing the audio properly, Andre. In any case, we've been having your, if guys, they want to have the full story, there is your own presentation, which is over there on the YouTube. You've sent it me yesterday, and we've been loading your
Fabio?
work. Yeah?
Fabio?
Yeah.
You cannot hear it? Is that what's happening?
No one.
Okay.
I think.
No, I can. Okay, I'm sorry. I can try and present the PowerPoint then if you're willing to.
Yeah.
I mean, if you.
In any case,
you want me to present? You want me to present
yeah, for
it?
sure. It would be nice if you can turn on.
Yeah.
And in any case, because I want to if I can say, please know that in the YouTube we have already posted your own presentation.
Okay.
You've been working. You've been spending all your Sunday on the recording the presentation, and so I want that the people they have your own presentation there. But maybe you can talk within a PowerPoint. We can discuss in a free way. You know, we are not. I'm sort of would say. Not fully a CalFAD professional, but I can use CalFAD technologies. And most of the guys here, apart from the guys from Computherm, they are not CalFAD professionals. So I would believe that it would be fine to make a general presentation with a PowerPoint file if you have it. I must say that you have very nice papers, not only in this field. There is another recent paper on the solidification of steel. So you have plenty of scientific work, which is very actual. Even in this difficult year, you've been very, very active and proactive. Please.
Okay, let me try now. I'll try now with the PowerPoint, and you tell me if you can see it now.
Yeah.
Okay, this is the PowerPoint. Okay, can you hear me?
Yeah, sure. And you can also see your slide presentation.
Okay.
So.
Okay. So the idea is to present you what I have been doing with the microloid steels using the CalFAD technique. So we are going to look briefly on the thermodynamics of carbonitride, and I'm going to show a little bit of how the CalFAD people have to do what we have done to handle this. And of course, the question you have is we are not in equilibrium in industry. So yes, we are not. So equilibrium is important, but we are going to discuss what happens when you have non-equilibrium and also how you can handle kinetics a little bit now using the CalFAD approach. And then I hope to present you a little outlook of at least my view of what's going to happen with these techniques in the future. So if we go back to the 50s, that's when people started studying these compounds, and a lot of them were studied because they were very hard and high temperature compounds. And so there's two lines actually, if you look. I mean, there's one line that is very much related to the compounds themselves, and the other line relates to the solubility of the compounds in steels. Of course, back in the 50s, there was very little use of microalloying, but then if we look into what was first published about these compounds, you see back in the 50s, people already knew that niobium carbide had miscibility with vanadium carbide, with titanium carbide. You see, this is the lattice parameter, this is composition. So this is showing that the miscibility was there and people knew that the cubic carbides were mixing. Then also they knew that, you see, this is so old that it's still columbium here. But then columbium carbide or niobium carbide had miscibility with niobium nitride, titanium nitride, and vanadium nitride. And this is sort of one of the big problems for the CalFAD and for the thermodynamics and for the solubility products of these compounds, because they are very complicated. I mean, you cannot, unfortunately, just assume that you have niobium carbide or niobium nitride in your steel. Some years later, this gentleman did a study, and they show this is if you look at the stoichiometry of 1:1 niobium nitride, and they show that most of what they seen was really deviating from 1:1. So they had a lack of, let's say, the interstitial element. So most common was here. And then back now in 1962, the first work on solubility came by Smith. And he just looked at the solubility product of niobium nitride in steel, and he got some real nice results. And I think he was very happy, and he was a pioneer there. And then the Japanese Mori, back in 65, I mean, he started looking now in his steels, and he found that he could not really reproduce Smith's result, because he had some results when he was able to make a steel without any nitrogen, and even then it was completely different from what Smith said. So he said, he had actually, when he had nitrogen in the steel, there was a deviation not only in stoichiometry but also on the composition. So that's when things start to complicate. Then Irvine proposed that, and I think most of you have seen this. I mean, instead of let's do it very simple. I mean, we just add atom by atom, and we assume that carbon and nitrogen are in the same place, and this is the easy solution. And he put all the data here. Now, keep in mind that this is log. So if there is this spread here in the log scale, this means it's a huge spread. Then back in the compounds, people start noticing that when you went low in temperature, the carbides were not fully miscible. I mean, if you look in the first figure I presented you, there was full miscibility. Now, if you look at vanadium carbide and niobium carbide, you see they are not really completely miscible at lower temperature. And this is what we see in steel. I mean, you see the niobium carbide precipitating in one moment, and the vanadium rich carbide or nitride is precipitating in another moment. So this was already a very interesting information. Now, enter 1970, Larry Kaufman invented CalFAD. He was almost killed because of that, because he sort of shake the basis of all the ideas that were around. And of course, it's not very big difference from the classical thermodynamics. If you look at this little corner of the ternary, which is this is iron, carbon, niobium, and you have here exactly the solubility limit of the carbide, and then I mean, if you work on a melt shop or if you work in steel making, normally you're used to using solubility products and not phase diagrams. So, sure. But it's all the same. It's all the same. It doesn't really matter. It's just a different way of looking at all that same result. Now, if you continue in this study, then back in the 70s, both Mats Hillard and Rudy, they did some very interesting work about this idea of sublattice, that you say, well, I can mix these elements. Yes, I can. But you see, titanium, niobium, and vanadium will only go in one side of my sublattice. And carbon and nitrogen and vacancies will go in the other one. So why don't I model this in a different way so that I can have the entropy model without the possibility of titanium mixing with carbon, because it's not reasonable. So this came out as this compound energy formalism, which is very much used in all the CalFAD modeling. And then Hiroshi Otani was the first one in 1988 to publish a model using a single crystal structure to describe both, or not both, I mean, austenite, the carbonitrides, and for titanium, niobium, and so on. So it was a big breakthrough because it enabled CalFAD to handle all the solubilities. You don't have now just a single compound called NBC. You have a variable composition compound. Of course, the problem was that Hiroshi had some errors in his experimental, because it's not, as you all know, I mean, in industry, it's not easy at all to measure the solubility of these things. Sure. So there was some criticism about his measurements, and then Palmieri came in '94 and he put together all the different solubility products, and you see it's a real mess. I mean, it has values everywhere. And of course, one of the reasons is because they are really not niobium carbide. So they are mixed with different elements. They have different composition. And so this is very difficult to describe just by looking at like if it was alumina, for instance, that we know this works very, very nice, or if it was silica. Here we have a completely different situation, unfortunately, for us. So a lot of people work then from 2000 on in the CalFAD. There's many good models. And of course, the solubility product also continue. And then if you look just at the work of Kirkcaldy, I think he got a prize for this work. I mean, this is what they measure with TEM on the occupancy of titanium and niobium and carbon and nitrogen as the temperature varies. And you see, this is very, very difficult to measure because this is all measured with TEM on actual particles. You cannot just do that outside of the steel. But you see the experimental values agree very, very well with what they calculated, assuming miscibility of these compounds. Then, funny enough, I mean, Palmieri in his paper in 94, he said, I see no carbonitrides. But fantastic, the best agreement his solubility measurements gave was with the carbonitrides theoretic product. So it's really quite conflicting. Then we see a lot of models coming out, and especially this is Karin Frisk, who was, she's from Katie Hagen, she's very famous in Sweden. And you see the agreement with the TEM measurements of Yazak are very, very good. I mean, the aluminum here is lost because they also measured the aluminum nitride, so they shouldn't really plot the aluminum here. But anyway, they plot it. And so the real proof is when you look at this TEM result, I mean, this is when the guy had the niobium steel with the vanadium. And so you have actually 4 possible extreme compounds. You have niobium nitride, you have vanadium nitride, you have vanadium carbide, and you have niobium carbide. And they measure in TEM, these are the black dots here, that they had simultaneously, as you all know, both the niobium carbide and the vanadium carbide, but they were not exactly pure niobium carbide. I mean, this is the composition in one side, this is the composition of the other one, and this is what they call a miscibility gap, a region where you cannot have a single phase. And this is indeed what we see. I mean, we see these different compounds with the same microstructure, or sorry, with the same crystal structure, but different compositions. And so once CalFAT was able to handle this, I mean, things became much more interesting for us. Now, the problem, I think, is that we also have a very, we love to use the simple approach. So if you look at the classical approach and you compare, I did this some years ago, if you compare, for instance, the thermocalc solubility product here with the value proposed by Palmieri, they do not agree, of course, because this is for the steel he used in his experiment, which had like 80 ppm nitrogen. So it's really impossible to assume that if you have 80 ppm nitrogen in this steel, you would have a niobium carbide pure. It's not going to happen. It's going to happen that you're going to have nitrogen in there. So the other question, a lot of people would like to use this Turk-Dogan carbonitride, but then again, this is very nice. You end up getting a little bit more complicated if you want to do it by hand. So you have a surface now because you have 3 compositions. But he fixed the stoichiometry here. So this is also not going to work very well. I mean, if you compare the values that you calculate using his model and thermocalc, for instance, or a good database, you see that they do not agree in all compositions because the stoichiometry is varying. When you have a lot of nitrogen, the stoichiometry is not going to be 0.2 if you have less carbon or if you have so this thing is a good approach when we didn't have CalFAT, but it's not very good anymore, I think. Now, you've seen this with PENDACT, so I'm going to go very quickly. I mean, when you are able to do the calculations, you get this sort of classical graph that we all use, and sometimes it takes a while to understand. I mean, we can get a lot of information when you vary the equilibrium conditions, especially the temperature, and you calculate what's happening. So you start with liquid, you go through the perithetic, this is ferrite, and then you see a precipitation of something which I call, just to make a nice caption here, titanium, nitrogen, carbon, but this is a mixed compound. But this is what we would see as titanium nitride precipitating at high temperature. As you cool down, you see niobium carbide precipitating. So if you wanted to hit this slab, you would say, well, I have to hit it above this temperature. Otherwise, I cannot dissolve completely this guy. And then you can see aluminum nitride is coming here. So I say, well, I don't have to worry about my aluminum nitride. It's going to be fully dissolved. And then you go into the intercritical region, and then you have cementite. Now, if you go to a little bit more complicated steel for an API 70, for instance, that is made by tube rolling, you have vanadium, niobium, and titanium to get the properties. And then you see the 3 different, I mean, this is written in Portuguese, but this is FCC. So you have the titanium nitride, you have the niobium carbide, and then you have the vanadium nitride, which is precipitating here to give you precipitation hardening. That this is very nice. This is equilibrium. And then if you look at the composition of this phase here, then you get very confused because you see this is the composition here. It's just presented on how much of the metals you have, titanium, niobium, and vanadium, then can go from 0 to 100%, or if it is a nitride or if it is a carbide. And this is varying with the temperature. So the equilibrium tells you that you start with a lot of titanium, and then titanium should be decreasing. Now, of course, if you look at the little particles that you have in steel, it's very difficult to imagine that they're going to be changing their compositions as time goes by. And of course, they're not. So what's going to happen is that something different from equilibrium is going to happen. It's not exactly in equilibrium, but these values are correct. So the question is, just we have to understand that this is the equilibrium composition, and it may not be exactly what you're going to see in the practical values. Now you have to be careful, because if you start to adjust the equilibrium values because you don't see them in reality, then you end up in a complete mess, because you have you don't have the thermodynamics right anymore. You have everything mixed up. So my suggestion is, let's keep the thermodynamics as it is. So I would say at this point, for the thermodynamics only, that the computational thermodynamics is able to give a very consistent prediction of equilibrium for all these carbides and carbonitride. And I can tell you this because we have done this for a huge number of different steels in Brazil, from rebar to IF steels to API steels, from thick plate to whatever, and we got very good predictions. So it works very well. So, and with the very different compositions and temperatures. And of course, this way you can also take in account the fact that you have high manganese or high silicon, and these guys are affecting the activity or the chemical potential of these elements, which you cannot do with the simple solubility product. So the question I want to leave to you is, does it still make sense to use just a simplified stoichiometric solubility product when you're doing either your alloy design or your process design? I don't think it does, but anyway, this is the question. Now, when we go into non-equilibrium, then I'm going to just mention 3 ways of doing this. If we're using DICTRA, which is diffusion modeling, we can start just by looking at secondary dendrites and say, okay, let's assume that this is just controlled by diffusion redistribution. And then we can say, well, DICTRA is very simple because it can only use one-dimensional diffusion. So you can use and have a planar, spherical, or cylindrical geometry. You cannot go very fancy. The Japanese normally use a triangular or a prisma or whatever. We cannot do it. We can only do so. What we did was just make a cylinder here and say, well, this cylinder is going to be shrinking into the interdendritic region. And so if you look from the top, that's what you happen to have. You have a cylinder here, and it's shrinking, and we're calculating the segregation. Now, to do this, you need good information on the dimensions of this cylinder, right? You have to know exactly what's the dimension, and you have to know the cooling rate. So the dimension is not easy. I mean, these 2 steels we sent to a colleague in Germany, and he has one of these huge microprobes. You see, this is just to call your attention, this is 2 millimeters here, this little bar here. So actually, this is like a 1 centimeter by 1 centimeter probe. So it's one of the nicest pictures I have seen in many years. So this shows you clearly in this steel, which is an A55F8, that you have manganese segregation, you have primary arms, you have secondary arms. This one is a high temperature processing steel in which we have a lower manganese, lower carbon, and we have higher niobium. And this is very nice because you see there's no secondary dendrite arms. For some reason that we are not going to discuss here, you're able to just have primary arms. It's somewhere between cellular and primary arms. And then we measure the dendrite arm spaces from here and from here. And then we calculate the cooling rate using those very old relationships that Suzuki developed back in the 1967 or something. I mean, they're very precise, and they give you a good estimate of the cooling rate. Now, we do 2 data. If I have the chemical composition of the steel, actually 3 data, the length scale, which is the dendrite spacing, and the cooling rate, I can use DICTRA. And this is what I calculate for the steel with the secondary arms. This is the start of the solidification, and then it goes all the way to the interdendritic region. And the blue line is what Dictra calculates, and the green things are measured by the microprobe. So it's not bad. You see, there's a recent paper by Strangwood too, which they did all. I mean, they did the microprobe very carefully in between here, and they show that it also agrees. Now, if you go to the HTP with the low manganese steel, you see the agreement is very good too. Now, keep notice that this is now the primary dendrite spacing. So this is now 600 microns instead of 200. And it agrees very well, but most important, it doesn't segregate as much. I mean, you all know, of course, but just preaching to the pulpit or whatever. But I'm just repeating, but that we have to be careful with alloy design, because if you design an alloy that does have a lot of segregation, titanium is going to segregate, niobium is going to segregate, and you're going to lose these elements. So maybe we should try not to use that much manganese, which is classical for us, but this is going to increase segregation and push our elements to the liquid, and then this is going to cause precipitation. This is now the Scheil model, which is a very simple idea back from 1948, I think. And you're all familiar with Scheil because we all learned Scheil in school. You assume that the solid is never having any diffusion and the liquid is perfect homogeneous. So this is very simple, and that is easy to handle with a simple routine in Kalfa. This has no dimension. This has no cooling rate. So this is just exaggerating your segregation. But we can calculate at what temperature the niobium carbide will precipitate in the liquid. And we see this is precipitating here, and the other still is precipitating here. So it's a little bit different. And the nice thing is that when you compare our diffusion calculations, which I must tell you, I mean, they take sometimes 1 day. I mean, this is, I always joke with my students that is one of the cases when real life is much faster than simulation. But on the other hand, real life is much more expensive than simulation. So if you spend 1 day with Dictra, it's not going to cost the same as it costs to cast a heat of 300 tons and see what happens. Yeah. So the models agree very well. I mean, I can see when the precipitation starts. In both models, they are fairly similar. So, and the important point I want to bring it to you is this way, I can do a calculation and I can estimate how much microalloying elements I'm losing. So if you go back to last year when vanadium was like, China has bought the prices of vanadium to the top of the sky. And you say, well, I'm losing vanadium or I'm losing titanium. I mean, this is not like losing a little bit of manganese. I mean, the price scale is completely different. Yeah. So you have to be very careful. I mean, there's no point in adding a lot of manganese, which is cheap, and then adding a little bit of vanadium and titanium and niobium, and then losing these things. It's not, it doesn't make sense. I mean, you get it in the heat analysis, but it's not doing what you're paying for. Sure. Sure. So at the end of the casting process, if you have a titanium niobium steel, for instance, what you have is this. I mean, they are beautiful, of course. I just exaggerated the size, but you have all these nice titanium nitrides, and I pick up some pictures from the literature. We also have some of this, but this one I just wanted to emphasize because what we are doing now is to model how they nucleate on the alumina and its inclusions, because they clearly nucleate in alumina, so you can probably do some engineering on what is going to be there to nucleate or not. But anyway, these guys mean these particles here with 5 micron, these are essentially lost titanium for microalloying, because this titanium, and this is also titanium carbonitride here in the interdendritic region. So this is lost. I mean, this is titanium that you bought, you added to the steel, very nice, it's in there, but it's not going to help you in controlling austenitic grain size. It's not going to reprecipitate to the coiling, so it's just lost. And this is our work, and we have here, you can probably see here in the corner, this little titanium niobium carbonitride. And then here you also have large, I mean, because they are large for affecting the microstructure, niobium-rich precipitate. So these guys are lost niobium. So you have to do something about this. Now, when you go to dissolving these things, you go to your plate or to your billet furnace. Of course, we want to dissolve them, but now what temperature should we use? So you use the equilibrium temperature. Should we go 50 degrees above equilibrium? And then we can use Dictra. And what we did was we did 3 different particle sizes. And we thought, well, 500 nanometers, half a micron is still a reasonable size to try and dissolve. And so this is the actual cycle that this plant uses. So they do preheating, heating, and then there's a soaking time. So this was measured with thermocouples inside the plates. And then you can see that it takes a long time to dissolve, and this is your niobium in solution. So you see niobium is increasing when you go, of course. So you end up getting some more niobium if you stay longer time, and you can actually quantify this. So now, if you look at the equilibrium dissolution temperature, is here. So it's not really getting all carbides dissolved. I mean, you have to wait until the larger one. So I have a little animation here. So by the time you reach equilibrium, this solution is not dissolving. If you go beyond, then these guys are dissolving. The black guy is gone. The red guy is now gone. And then finally, the blue guy is gone. I mean, of course, there's no chance you're going to dissolve something that is 5 micron, and it's going to be too expensive. And it's so distributed in the segregation areas of the plate that you're not going to have real good effect anymore. It's segregated. Now, there was one question back some years ago whether there was diffusion in the carbonitride or not. Luckily enough, this is not the controlling step, so it doesn't matter. Luckily enough, the diffusion process is controlled by austenite, so it's not a problem. Now, when you look into the precipitation in austenite, we have 3 ways of looking at it. I mean, you can look with what I call a shell-like model, in which you assume that the particles will never change their composition once they precipitate, but the austenite is fast diffusing. So which is not very different from real life. Then you can do actual diffusion with a single particle, which I'm not going to discuss. And then you can do multi-particle, different sizes, including nucleation and diffusion. So which is, of course, the ideal, but it is much more complicated. So if you look back into that still that I showed you some time ago, where you had that very complicated composition, back in 2008, I mean, the international international IMET, I think, was in Italy. And our colleague presented this work in which we did the shy one. Then instead of having this change where you have one titanium particle, then precipitating another different phase here, and then the third phase, what we found was we had a phase that was precipitated, then at a certain temperature, boom, it started to grow at a different rate and with a different composition. And then finally you had your vanadium. And then when we calculated, this was the equilibrium composition, if you recall, titanium going from very high to very low, niobium peaking, vanadium. And now what we calculated is very interesting, because as you cool down, instead of having that variation, we have now titanium is going down, fine. Nitrogen is almost constant. And then at a certain point, the composition changes dramatically from titanium nitride to niobium carbide. And this happens because you have a miscibility gap, as I showed you before, in 4 compounds with vanadium. Now I'm showing you niobium, nitrogen, titanium carbide, and the miscibility gap is here. So our precipitate is starting here, forming mostly titanium nitride. Composition is moving this way, and then it touches the boundary of the miscibility gap, and bing, it forms another one, which is this one. And this is what we see, of course. I mean, this is when you have these nice caps of niobium carbide on the top of titanium nitride. Of course, this is, he did the TEM, he analyzed them. I'm not going to show this. Now, if you go into precipitate in the solid state, the problem is you could do it by Dijkstra, but then you're doing diffusion in one single particle. And of course, you're looking at the precipitate distribution. That's what's really important for us. So what happens is very different. I mean, you have multiple sizes growing, different locations. So you have to know the volume fraction, you have to know the mean size, the size distribution. Then you can know the spacing, and hopefully you'll be able to guess the effects. And it's not easy to guess the effects at all. Now, you can do, if you look at how this has been handled, I mean, there's a great work that everybody uses, which is Dutt and Tellers back in '87, in which they took the classical nucleation and growth theory. So the thermodynamic center here, this is the solubility product, And then all these things are just nucleation and growth phenomena, diffusion, nucleation factor, and then he calculates the time for 5% precipitation. And it sort of works, it's nice. But now what happens? I mean, since it doesn't work perfectly or very well, then people say, well, maybe this constant A, which is just a nucleation constant, should really not be a constant. It should depend on the solubility product. Maybe B, which is somewhere here, here it is to also depend on the solubility product. Now, how could a constant, which is coming from the nucleation theory, depend on the thermodynamics of nucleation solubility product? I mean, it's supposed the theory says it should be here, and now we have it also here and here. So the question is, are we doing curve fitting or are we doing theory? So it's kind of it sort of exhausts your ability to make predictions. Not that you cannot reproduce the results that you get. I mean, you can get perfect reproduction of your experimental results, but when you have a new steel, will it work? Probably not, because you have to go into extrapolation and your theory not robust enough. So what we do, I mean, you also saw that in PANDAT, you have models now that take in consideration the classical nucleation theory, very classical, but instead of doing it just by hand waving, now we have the actual free energy changes are coming from the thermodynamic databases. The actual diffusivities are coming from the mobility databases. So this is very robust. And now we need another set of properties which are not very easy to know. Grain size, dislocation density, and interfacial energy. So you have to know all these variables to make very nice predictions of volume fraction precipitated as a function of temperature. This is, we calculated for aluminum nitride in ferrite. So it fits very well, but it takes some work to get this data properly. And this is what is done by Prisma, which is another software. Now, you have all these variables, and I'm not going to all of them, but you have to be careful because interfacial energy in particular, if you recall this from our basic classes, I mean, the nucleation theory, you have the critical radius and you have the nucleation barrier. Now, the critical radius depends directly on the interfacial energy. The nucleation barrier, how tall it is, depends on the cube of interfacial energy. The nucleation factor depends also on interfacial energy. So, and then now if you go, okay, it's just a question of measuring an interfacial energy. Now the problem is that everybody who measures nucleation or who measure interfacial energy, normally they do it by measuring nucleation and growth. So actually you fit the interfacial energy to experiments in nucleation and growth. So how do we do? So now the new softwares, I mean, they have more fundamental models to try to predict the value of this so that you can be doing calculations that are more predictive. And because look at this, I mean, this is a table for just interfacial energy between austenite and carbonitrides. And this is by no means exhaustive. I think if I search more in the literature, I would find more results. Then it goes from 0.1 joules per square meter to 1.5. So it's crazy because with these values, what happens is, I'm going to show you some results. They have a profound effect on how fast the things grow. And if you're doing a presentation or if you're doing a simulation for industry, then the question is, or for paper, for industry, they will throw you away. But if you're publishing a paper, you can do the calculation. And then if it doesn't fit your experimental results, then you say, wow, it doesn't fit, but if I use 0.5, it will be perfect. And then you say, I use 0.5 because this is what the reference 106 proposed. And then people say, wow, you're a genius. But then the question, why didn't you use 0.1, 0.3, 0.2? So you have to have a robust way of actually not using this as an adjustment parameter. I mean, you have to have a theory that gives you a correct result to use. And this is the values of sigma for at 900 degrees for niobium carbide, depending on carbon and nitrogen. So you see, it varies. So good, we have a model to calculate. And then I take a very old paper by Le Bon. I think if you work with microalloys, you're probably familiar with this. They did a wonderful work on precipitation of niobium carbide. And this is the niobium in solution, the vertical axis. So, and niobium precipitated. So it goes from zero, all niobium is in solution, 100% all niobium is precipitated. And then this have this, and this is time. So they have the precipitation curve for strain-free austenite. So you go from all niobium solution for all niobium precipitated. And of course, we are really interested in these curves here, but these are for deformed austenite. So we're going to look this in a minute. So let's see how this behaves. And then if you go into Prisma and you vary the interfacial energy from say 0.2 to 0.54, this is the volume fraction or the niobium in solution versus time. And you see the experimental results of Le Bon are these triangles. So the problem is if you fit, you can do anywhere. I mean, you can go, if you go from 0 to here, 1 is probably going to be here. So you can fit any result. If you have any result, you can fit. So now if you use the Prisma result, which is theoretically calculated without any adjustment, then you get a fairly good. I mean, it's not perfect, but nothing's perfect in life. So you got a good agreement, and this works. And why can't you not just fit the interfacial energy? Because it's not just a question of volume fraction or niobium solution. See, this is the number density of particles that you calculate. And if you change the interfacial energy, the volume fraction and the number density and the size distribution changes completely. So it's not a question of saying, well, I'm using just a little adjustment. You're changing completely the precipitation. So you got to be careful with this. Now, what can we do in multi-particle simulation then? You have to increase now. If you want to do deformed austenite, which is what we all want to do, you have to consider that the diffusivity is going to be increased because you have a lot of dislocation. Somehow the nucleation barrier is going to be lower because the material is deformed. I cannot, the model is not good enough to consider that you may have heterogeneous nucleation in other particles. And I cannot do interface precipitation yet. So I have to do it in austenite. But then we did, the first effort we did was we got some literature about precipitation in microalloy steels deformed. So we got Akamatsu from Nippon Steel, which is very good. We got Le Bon too. And we said, okay, let's see if we can fit the different values of interfacial energy. And we got like a curve that gives you a relative nucleation barrier. So as you deform the steel, the nucleation barrier for the carbonitride decreases. And then I can calculate values that are very close to what Le Bon shows. And with these values, I can also, this is now volume fraction, sorry. I can also take 5%, for instance, of precipitation. And then I can make all sorts of interesting calculations. I can look at the size of the particles versus time. I can look at the size distribution, which is very important, versus, so this is frequency, this is size. So you see it goes coarsening with time, even at 5 to 100 seconds is already coarsening, so you have to be aware of this. And then we can try also to calculate now the niobium in solution, which is the real niobium in solution, because you're considering many particles with different size that are precipitating in different locations. Now, if you try to use it in industry, it can be interesting. So this is now on the left is the same steel, the A588 that I presented you before. This was heated in the plate furnace at 1200. And this is our 5% precipitation curve. Here, a 980 temperature of non-recrystallization. And these are the double deformation tests for recrystallization. So you see, you can say, well, maybe it agrees well with 5%. I don't know, because when you do a PPT, a precipitation time should be a PTT, precipitation time temperature, you have to define what is the volume fraction. So you can say, well, 5 is a good number because everybody uses 5. So I think this is fairly good. But now if you look at the higher niobium, lower manganese, we don't have a very good agreement. I mean, this is moving from, let's say, some 0.5 seconds to 5 seconds. So if you're doing thick plate mill, this is not a good prediction. So we have to improve. But anyway, the question is whether double compression is also working correctly. Now you can also, with this information, you can also use more sophisticated understanding. I mean, you can go back and say, wow, but I'm not really so worried about what is the volume fraction. I mean, this is not all that interests me. I'm also interested, what I'm really looking at for a microalloy steel is what is holding the austenite grain boundaries. I mean, and this is not just the volume fraction. This is the force that the precipitates can do. And back to Zener, I mean, Zener said that this force was proportional to the volume fraction divided by the radius of the particle. So Prisma can calculate this. And then I can plot here for one of these Verving's steels. I mean, this is a wonderful paper. They did a fantastic work. And you can calculate the Zener force, and you see it's going to increase, and then you pass to a maximum. And then as it coarsens, it's going to decrease. And then you can plot the double compression results he had. And he said, recrystallization stops here, which is fairly close to the maximum. It's not perfect, of course. And then it starts again somewhere when my force is decreasing. So is it going to be something that you're going to put online to control your rolling mill? Of course not. But is it going to help you to understand how to design your alloy? I think it's going to help a lot. So in summary, I mean, because you're probably all tired, it's late in the afternoon, there's a Prosecco waiting. So so I think an equilibrium is very well determined and reproduced using CalFAD, and for microalloying steels in special. So I don't think we should use anymore these effective solubility products unless you're just controlling the production. I mean, if you have a steel that you have done many times and you want to control the production, you can look into your statistics, use artificial intelligence, or use whatever data mining, and then you can derive all the parameters but without worrying about thermodynamics. But if you want to develop a new steel, this is not going to work. So you have to use robust techniques. And I think computational thermodynamics is this tool now. Now, the solidification modeling is very, very important, because when you look into the cost, I mean, it's not just a question of designing your steel, but designing an efficient steel that you don't lose your niobium. I mean, I have a case, I couldn't show you, but I mean, I have a case in which we had vanadium in the dendritic solidification precipitate. So you say, well, but vanadium normally only precipitates at 900 or 1000. Well, it depends. If you have a lot of segregation, you can start losing vanadium at the start of the solidification. It's bad enough. So then you say, well, how can this company make these plates which my client buys with this composition and I cannot make it? I make the same composition and I don't get the properties. Well, look at the segregation, look at how much effective solutes you have. It will make a big difference. Now, one-dimensional diffusion, it's very useful. I think in special for solidification and for dissolution, it's very useful. I mean, dissolution was a big game changer here, because when we understood dissolution, we could trim the process much better. And then classical nucleation models like Prisma and like Pandat showed you before, they also have this model, and our Ernst Kozernski in Austria also has this wonderful MatCalc. So this is a real fantastic avenue. I mean, we're going to improve it, and they are going to improve the models to calculate interfacial energy. So this is going to be real the future, I think. We're going to be able to tie these things, and maybe in 5 or 10 years, really understand well what's happening and make optimized steels. So I think the real way is not trying to improve, just adjusting our empirical equations. I mean, we should try to interface these more sophisticated models, which you all know, I mean, they are accessible. They cost less than a microscope. And but of course, since you have to involve information technology people there, then they put all the limitations when you want to buy it. If you want to buy a microscope, it's easy. If you want to buy a thermocalc or a Pandat, it goes through IT, and IT is very picky. Anyway, but if you do this, you can couple thermodynamics to whatever model you think is better. Python is easy for the young people, and you can do this very easily. So I think this is the future. So I would like to first thank CBMM and the Brazilian steelmakers for all the discussions and the projects we worked together that made possible to have these ideas. And also thank you for your patience, and hope that we can have interesting discussions in the future or in the present, whatever you prefer. Thank you very much.
Thank you, Andre, for your fantastic lecture. It has been very enlightening and very interesting. You've been talking for some 40 minutes, but I think to develop all the concepts, we would need a little bit more, I would say, at least half a day. But the point is that truly you are one of the masters. I mean, because you have both the knowledge for the experimental work, you know how to deal with the real steels. You know, I think Brazil is something special with it. You have the niobium producers, and so you are something that it is rather unique, because of course the young people, as you mentioned, they could be able to grasp merely everything about computer and about software, but the point is that they should understand the physical basis of that. So my point is also that, generally speaking, it's increasingly difficult, at least in Italy, to have some people that at least grasps something, you know, about the concept that you can get from a microscope, not necessarily a scanning electron or a transmission electron microscope, but even by the microscope, and then about computational thermodynamics. So most of them, they tend to rely on to general softwares, which are not enough for modeling steels. So I think this is something very nice to study. And, you know, of course, reading a paper is different from listening to you. If I might say, this has been particularly effective, even more on the recorded, everything worked well. And I must tell all of you that we've been recording. If I won't have troubles, I will be able to have the registration of this very nice talk, and with a very nice introduction. And there are many points that would be interesting to develop. And one of the points is that how to introduce young people to both the words. Otherwise, so they should be good in computer using, so maybe the future is Python, maybe the future is using both, like is now Computherm is proposing, so both computational thermodynamics with databases, and so on, because otherwise the risk is that someone would just use artificial intelligence and try to model everything, which is the tendency now for Industry 4.0, and this is a mess for myself, because I believe it would work for companies making some 30 or 40 kinds of steel, but for companies making 1,000 of different kind of fabrication standards of steel, like special steel companies, would be completely a mess. So thank you, very enlightening. And I wonder if there is any kind of question from the participants. I think that everyone is, thank you for, especially from the people from companies, because myself, I'm privileged, I'm already home, but maybe one of them, they must switch and get to their dear ones. So I hope that in the near future, Andre, but truly speaking, we will be able to communicate, because there is plenty of activities to do. I will try to rewrite some of my possible proposal, and I'm really very happy to have you here, and that's really all. And I thank also everyone. I thank also Zhang from Computherm for allowing us this nice afternoon, and I also thank all the people from ABS Steel, from Christophe Stocchi to Benjamin, and to my former students, Amsterdam, and of course my wife Francesca. Okay, and then that's nearly all, and because she's been busy all the day to manage both the business, the standard business activity, and also the guys in France, Christophe and Benjamin. Thank you for joining us there from ABS Steel Design Center in Metz. So
thank you for the organization.
Okay. Thank you.
Thank you.
Yeah.
Thank you.
Thank you. And I'm really pleased to have you here. It was really enlightening. And I must tell you that this has been even more interesting with the recorded lessons, Andre. Okay. Thank you again.
Okay. Thank you.
And
Thank you all.
And thank you, Professor. Yeah.
And enjoy your Prosecco now.
Okay.
Take care.
Yes. Okay.
I have to go back to work. Bye.
Yeah, have a good day, and you have a good evening, all of you. Okay. Goodbye.
Thank you.
Bye.
Goodbye.
Ciao.
Bye.
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 Bye. Devo vedere di chiudere la conversazione, interrompe la registrazione.